Yes, yes, Dipro, it is. And it's this so yeah, so there are other problems that have been shown to be PPAD complete in say subsequent years. I mean, this is a relatively newer result compared to when when PPAD completeness was actually formulated and so on. The notion of PPAD as a class and completeness was a work of several decades, and today we will sort of briefly touch upon that, and as to how much sort of time and thought actually went in to develop that. Um, so in fact, this sort of um, so the PPAD completeness here in sort of fair division kind of problems, you will it's sort of giving out the conclusion of the story, but I guess all of you already know the story. Part of it is that we will see that these problems that we have looked at, Nash, Brouwer, and so on, they basically are the canonical problems of this class PPAD. And we'll see how that is, that they precisely capture the essence of the class PPAD, which means that they are both a member of the class as well as they're as hard as it. In fact, there are applications of Sperner. Sperner can be used to give solutions to this, fair division problems and so on and so forth. So in a way, that completeness, PPAD completeness, sort of indicates that being able using Sperner or Brouwer or Nash, but it just so happens Sperner is the combinatorial tool by which we do it. We can solve this fair division problems also. And one of the applications, a very small application of Sperner, I intend to teach. I think most likely tomorrow is pertaining to that. Tomorrow, if we get to time, otherwise at the beginning of next week's class. Okay, all right. So good. Just let me. I'm going to use my iPad to show the. Okay, so where were we? We saw last time. We were basically we stopped by the introduction of this problem called Sperner. Now, why Sperner came about, I just told you that Sperner was a tool by which Brouwer was shown, like the Brouwer's theorem. When I say Brouwer was shown, I mean, I'm using the term Brouwer both as the name of the theorem, the result, as well as a problem. So just if you're just sort of keep up with that kind of abuse of terminology, let's say. But the point is that there's a proof of Brouwer using Sperner's lemma. And yesterday I shared a lecture note which basically describes that. Okay, so this is where Sperner sort of spiritually shows up. That's intuitive. That's the reason why while discussing Nash and Brouwer, which we know are connected because Brouwer's theorem is used to prove the Nash's theorem. It turns out we have this third result from combinatorics, which is that the Sperner's theorem. Okay, and I emphasize the difference between combinatorics, geometry, and combinatorics versus topologies, because I want you to sort of at least appreciate, at least notice that these three problems are from three different universes of mathematics. And it really, I mean, there's no reason why one would, if you didn't know these connections, why any of this would be sort of connected. So that was part of the ingenuity of the proof when they were first, presented. Okay, so briefly, let's recap what is Sperner's theorem, Sperner's lemma. So I have said that Sperner's lemma is already defined for higher dimensions. You can define for any number of any dimension d. We are dealing with, for the purpose of our presentation and all, for two-dimensional Sperner. Now, Sperner works on not necessarily a grid like this. It's defined on simplex. Okay, a zero-dimensional simplex is what is a point. One-dimensional simplex is a line. Two-dimensional simplex is a triangle. Three-dimensional simplex is a tetrahedron. It's this three-dimensional triangles or object. Okay, and in higher dimensions you have sort of d-dimensional tetrahedron and so on. So it's called d-dimensional Sperner, d-dimensional simplex. Now, The general statement of Sperner will say that take a d-dimensional simplex, use d+1 colors. So in this case, we are using two-dimensional Sperner, so we will be using 3 colors. And there's this idea, this notion of a valid coloring of the edges. Okay, edge means the outer boundary. Okay, the notion what constitutes a boundary in higher dimension changes analogously. Okay, so those are the things that I'm not going in. But for this particular example, the valid coloring is of something like this. That you say that the bottom. Okay, yeah. So this part, this here, it can have all other colors, one of the 3 colors, but no red. This portion will not have a blue, and these 2 remaining sides will not have yellow. Okay. Okay. I also shared a nice video of the proof of Sperner's in 2 dimension using that triangle thing. YouTube. It's a really short video. Please do watch it. Okay, it's quite interesting, and it's something like it should inform you at least. Okay, so we could have used the grid sort of is helpful here because of the way we will extrapolate this grid onto the Nash diagram of those the kicker and player game that we saw last week. So I'll get to that. So this is why I'm using a grid type thing and not a triangle. Nothing's like particularly special regarding that. Okay, so we color it in this sort of way. So this over here, it could have been any kind of a coloring here on the outer edges, does not matter as long as you avoid yellow, as long as you avoid red. And then inside, you can color the vertices in any way you want. Okay. Now, let me say this about this particular grid. You are also assuming that these grids are somehow triangulated. Okay, like this. Let's say it could have also been this, the other way around. It could have also been like this, but whichever way you orient this sort of thing, you assume this way. You assume that sort of triangulation to hold through all of this. Okay. Now, okay. Then Sperner basically says that no matter how you color the internal vertices here, there are always odd number of triangles. So the triangles here are assuming these sort of implicitly using these phantom edges, which are not part of the grid diagram, but you imagine that they exist. Now, when we use a 2-dimensional Sperner, those you don't have to imagine that they are triangulated or not, because you're actually using a triangle only and creating smaller triangles within it. Over here, we are assuming that we have these lines and so on. Okay, and then so here is one colorful triangle. Here is one trichromatic triangle. Basically, I somehow tend to use the word colorful almost interchangeably. So here, because we're using 3 colors, colorful means all 3 colors are used and so on. So over here, you can see that there are actually 5 of them. Okay, so this is what Sperner says. It's a parity argument that not only such a colorful triangle exists, that itself may be surprising, but the fact that an odd number of them exists. Okay, the same result holds in higher dimension. You talk about higher dimensional simplices, and a similar sort of a colorful sort of object exists within that structure. Okay, sorry. Okay. So basically, and I said this is just a matter of fact as of now for you. And this thing, I have provided a resource that using Sperner, one can show Brouwer. So there is let's briefly sort of go over this and let's see. Okay, so let's just say that, so this, the diagram of the direction fields was, if you remember, was that kicker and goalie game that we were doing. And these arrows are basically, the existence of these arrows show that somebody, either the kicker or the goalkeeper, has a deviation strategy, right? And whoever has the deviation strategy, that person's sort of arrow direction, this f of x minus x, let me just use it. So F was the capturing the deviation strategy. So, and unilateral deviation, if you remember. I don't understand. Okay. Strategy. So the direction, this quantity, okay, this basically says the X is the mixed strategy profile. This captures the deviation strategy from this thing, the unilateral deviation. So the difference of this basically say which way should the deviation be, okay, meaning which direction does it give me, captures direction of improvement, okay. Improvement. Okay, and so if you recall, this was the sort of the color thing that we use, color scheme, where so this, if the arrow was pointing in this direction, we used yellow, and this direction we used blue, and this direction we used red, and that's the way it was. Okay, all right. So and then we interlay sort of just replace this grid on top of this colored diagram, and what we are trying to identify is this fixed point. And we know the fixed point also implies Nash equilibrium because of this connection between what the F function represents. Okay, so now how do we identify the grid? How do we identify the precise point, the location at which this happens? We have talked about that in this world, in this sort of thing, we talked about the epsilon approximate fixed point, because the point might actually be an irrational point, and then we would not know how. I mean, Sperner would not necessarily be able to find it. Like, we don't know how to meaningfully talk about it, because Sperner is basically a combinatorial this thing, and we can't quite express irrational points in that in sort of that framework. So we sort of do this. We create this, let's say, the smaller triangulation and so on. So the size of the triangulation is captured by this quantity epsilon. Okay, so smaller the epsilon, the idea is the smaller the epsilon, the smaller is the grid size, and thus smaller is the grid size, smaller would be the triangle. Correct? Okay, so and with increasingly smaller and smaller epsilon, we basically zero in on the precise point at which the fixed point lies. That's the idea behind this. So for a previous step, for example, if the fact is that, okay, the fixed point lies in this triangle, okay, but this triangle is still fairly big, I don't know exactly which point it is, you take a smaller epsilon, triangulate it even smaller. That again would sort of, Sperner would imply that there exists a fixed point, perhaps inside that smaller triangle, and so on and so forth. And so ultimately, you actually zero in on the epsilon sort of arbitrarily close to zero will tell you that where the fixed point lies. And that would be an approximate fixed point, epsilon approximate fixed point, and a corresponding epsilon approximate Nash equilibrium. Okay, so now the question for Sperner, so the Brouwer's input is basically a function, the domain from which the function is defined, the function is continuous, and the answer, and the domain D is convex and compact, and the question really is, what is a fixed point here, right? Okay, so similarly in Sperner, the input is a grid of size 2 power n to 2 power n. This so n is some value, and so you have it's a square grid for the purpose of this thing, simplicity. And the question is that the boundary has some standard coloring based on the type of rule we described before, and the internal vertices are colored arbitrarily. However, what are those actual colorings is given by, not by, like, I don't write it down explicitly, because writing down this grid itself has has an order 2 power n number of points. So writing down all the vertices and what their colors are would basically require it. So any vertex here is basically specifiable by its x coordinate and a y coordinate. If you think about this being the y coordinate axis, and this is the x coordinate axis. So any point can be precisely specified by a x and y coordinate, but there are order 2 power n number of such points. So writing that down itself would be of exponential size, right? The input itself is exponential in n. Okay, so therefore we imagine that there exists a succinct representation. Okay, and then the succinct representation is via a circuit, and the circuit basically tells you give the circuit the x coordinate and the y coordinate of a point, and the circuit spits out what is the color, one of the three colors of those internal points. Okay, now you can also basically give the color of the outside lines, but the outside grid boundary, but that's sort of implicit that okay, I can know, but still, one can also capture that, because imagine that all the points on this line are basically have zero coordinate, and they have they have a variable x coordinate value, but this y coordinate is zero, all zeros and so on, and this analogously the opposite for this. Okay. Now, the question is you have to output a trichromatic triangle. Okay. Now, Sperner says such a triangle exists, right? Question is how to find one. Is it clear? Okay. Now, tell me something. If I had given you the same question without this circuit, just explicitly given you a graph, could you have found it? Would it have been easier?
I think just a grid graph, right?
Little again, please. Your voice got a bit muffled.
Hello.
Yes. But repeat again.
I think a grid graph, right?
Yeah, assume it's a grid. Yeah.
I said when you talk about giving a graph, the grid graph, and we want the like the 3 cycle having 3 different colors. That's what we want.
Yes.
Hello.
Yes. So the question is to find such a triangle. You know such a triangle exists. Find one. Okay. So think about it. Would this problem have been easier if this grid was explicitly known? Okay. Now, but the question is given in terms of this circuit. Okay. Now, why is this circuit a succinct, or when we say succinct, what we mean is a compact representation. Okay. So basically, the circuit requires only 2n bits, right? X requires n bits to represent a coordinate in this grid. Y requires n bits to be represented, and just it gives you color. So it's one of 3 possible values and so on, right? Okay. But this representation would have been much more extensive and a much more space-consuming representation involving exponential number of objects. That's where the succinctness or compactness comes in. Okay, so just while you think about this, that would the question have been necessarily easier to find a trichromatic triangle if the representation is explicit? Let's just sort of recap what these classes were: function NP and TFNP. So all these questions fall into this framework of search problems. The answer is sort of, we know Nash equilibria exists, Brouwer's fixed point theorem exists, Sperner's coloring exists. But what we are interested is in finding one such solution. Okay, so that's what a search problem is. We need to find a solution, not necessarily just decide whether a solution exists or not. Okay. Now, a search problem is total if there always exists a solution. Okay, that's what this is. For all x, there exists y such that xy is in the relation RL. So the relation RL is basically a set of pair of strings where the first string encodes an input instance and the second one encodes a solution to this. So a pair x and y is in this relation RL, set RL, if and only if y is a solution to x. Okay. Okay, I have gone a bit early, just got split. So, okay. So now we will define, okay. So notice something, we talked about this last time, but it's worth repeating. So you agree that the search problems are somewhat different from the kind of questions that we normally study in NP, which are decision question, which is like, does this problem have such and such property, right? Like, for example, SAT. Does the formula have a satisfying assignment? If the question had become, find me a satisfying assignment, if it exists, that would be a search version of SAT. Is it okay? But when we just generally talk about SAT, what we are talking about usually is just answering yes or no, satisfiability or not. Okay, all right. Now we know, is SAT part of the total? Is the problem search SAT, right? Find an assignment. Is it total?
It's total, like finding all such assignments, right?
No, read the definition of total. Total means a search problem is called total if and only if for all inputs there always exists a solution. For all x, there exists y.
But we're talking about the SAT problem.
Sorry? 7?
We're talking about the SAT problem, right?
Yes. And the SAT problem is, given an assignment, decide whether there exists a satisfying assignment. The search version of SAT is given a formula, not only decide whether there exists an assignment, satisfying assignment, but find one. So clearly, we know that there are formulas that have no satisfying assignments. Correct? We can come up with formulas for which there exists no satisfying assignment. Correct or not? So search SAT cannot be total because of the simple property. There are sort of Boolean formulas for which there cannot exist any satisfying assignment. Total, the definition of total search problem literally is that for any instance, there always exists a solution. Okay? So that's something to keep in mind.
So when I see, when we say about the y, that is the yes instance, right? Yeah, okay, now it's clear.
So the point about that total is that by default, a problem is total. A search problem is, firstly, totality, this term total is only used for search problems. Okay? A search problem is one where you can have instances where no solution exists. All we are saying is X and Y, this relation RL captures all those pairs and solutions, all those pairs where Y is a valid solution to X. So if you think about search SAT as an example of this problem, it would basically be a pair of all formulas which have a satisfying assignment along with their satisfying assignment. And one formula can have multiple satisfying assignments. So phi, which is satisfiable, and paired with all of its satisfying assignment. Those pairs would be part of RL. Okay? Now,
clear now. Thank you.
Okay. Okay. Now, if X does not have a satisfying assignment, okay, this relation RL says nothing about that. See, because it's an if and only if condition. Yes, agreed? So the point is, therefore, searching the SAT, the search version of SAT cannot be total because there are instances for which we know that there is no satisfying assignment. So that XY pair, so for all those X's for which there is no satisfying assignment, there does not exist any Y which will be part of this RL set. Yes? Okay, that's what I mean. Okay, so now let's try to excerpt what this actually means in a little bit more sort of a mathematical term. So we define this class FNP. Its a full form is functional NP. So a search problem L is said to be in FNP if and only if there exists a polytime algorithm AL, okay, and a polynomial function PL such that for all x and y pairs, this algorithm AL, x and y, if algorithm when applied to x and y says yes, meaning the y is a valid, so this algorithm basically ends at says yes, equal to 1 is to be interpreted as yes, if and only if y is a valid solution for x. So suppose this is a search sat algorithm, okay? So you feed in it, you give it a Boolean formula x, and you also give it a Boolean assignment y. The algorithm says yes if actually that y is a correct assignment, is a satisfying assignment for the instance x. Okay? So that's an if and only if relation. The algorithm will say yes if this is actually a valid satisfying assignment, and if there exists a valid satisfying assignment, okay, like this is this thing. For all such valid satisfying assignment, the algorithm will always say yes. Okay? All right. Now, this is this interesting part. Now, what we are saying is for all input instances x, if there exists a y such that y is a valid instance of RL, okay? What this was, correct? Just a sec. Sorry for the disturbance, okay? So yeah, so for any x for which there exists a solution, meaning this condition is actually satisfied, there also exists a solution which has polynomially bounded length. Okay? This is the essence of NP. That not only is there a solution, but there's a polynomially bounded solution. And it's this polynomially boundedness which allows me to check in polynomial time whether this is actually a valid solution. Right? That's the essence of NP, right? The intuitive understanding of NP that we have. No? Okay. So, okay. So with that in mind, do you have any questions? These sort of things will get more and more clearer as you sort of think a little bit. Maybe at the beginning it seems a bit too abstract and all, but you'll get used to it. Okay. So total FNP are those subclasses of FNP. Is a subclass of FNP. It just contains all those languages of FNP or the problems in FNP, which also happens to be total. Okay. All right. So, do we agree that Sperner, Nash, Brouwer, all these problems are at least in FNP? Sorry. Not sure what happened. Do you, yeah. So do you see that why these questions like Sperner, Nash, Brouwer, they are in FNP? Do they fall into this framework is what my question is. Like, can you recast, because the definition of FNP is this, right? This is the definition of FNP. For Sperner or Nash or Brouwer to be part of this class FNP, there must be this relationship that there exists a polynomial time algorithm for the corresponding problem and a polynomial size function such that for all solutions of this problem, of any instance of the problem, the algorithm will answer yes, and it's an if and only if condition. And the second condition is that for all instances, as long as there exists a solution, there's also a polynomially bounded solution. What? Is it clear?
And for Nash, the second condition, how is that hold?
For Nash, the second condition is?
Yeah, the second one, for all x that exists, so y that thing.
Okay, for Nash, is it clear? What was your comment? Please repeat again.
Like, how does this second one hold for Nash?
Okay, so so Nash is saying that here is a game, there exists a Nash equilibrium, right? And the question is that how to find the Nash equilibrium. That's the search property, right? Following this. So what is the RL relation? The RL relation is this: a game description and a Nash equilibria description, right? Those are the pairs that constitute RL. Yes? Okay. So now,
is it just Nash equilibrium, or is it a epsilon approximate Nash equilibrium? Because only then we can have bounded size in the.
Yes. Okay. So when I am talking about, okay, good point here. When I am talking about Nash and Brouwer here, I'm basically talking about epsilon versions of Nash and Brouwer. Okay, so yeah, so just let's take that this thing. Okay, assume it. So yeah, I said this last week a bunch of times, so I forgot to emphasize it. As of now, whenever we are talking about is imagine just the back of your head, know that we are basically talking about the epsilon version of this. Okay, yeah. So Sanjay, do you know why is this in FNP Nash?
No, I don't know how to check if something is epsilon close to a Nash equilibrium.
So you know that if something is not Nash equilibrium, we know that there exists a deviating mixed strategy. That's the definition of not Nash equilibria, correct? And we also saw a property, which is that there exists a mixed strategy deviation. There's also a pure strategy deviation, right? So that pure strategy wise, you can always check, right? Because that is part of the game description of the players. So for each individual player, you can plug in one pure strategy and see, does this pure strategy give me an epsilon deviation? So what is an epsilon deviation? It's not a strict improvement, but adjusted with this minus epsilon. Okay, so with that in mind, it is polynomial checkable.
Excuse me, ma'am.
Yes.
Can you please repeat what you said about there exists a mixed strategy deviation implies there exists a pure strategy deviation?
Okay.
Because
so this was done 2 weeks ago or something, that CMI class. So I left, or like it was several weeks ago. That's right. So the lemma is, and this is very useful, you kind of have to remember this, okay? If X, which is, it's a mixed strategy profile, please remember the notation. Okay, I don't know how to move this thing from here. You know how I can get rid of this palette. Okay, that didn't be. Okay. If X is not a Nash equilibrium. Okay, for simplicity, I'm just talking about Nash equilibria, not epsilon Nash equilibria, but the result holds analogously, okay? It's not a Nash equilibria. Then by definition, this is not a statement, this is by definition, there exists a player I and a mixed strategy for this player I, correct? Such that when that player deviates from that game, that mixed strategy, he wins, he gets a strict improvement. Correct? This is the definition. Now, we can show there exists a strategy, let's say AJ, A, in the strategy action set of this player I, okay, such that this action A is in the support of this strategy XI, that the one that gives him a strict improvement, right? Within that, this is a strategy. So what is the support? Are all those actions which have non-zero probability under this mixed strategy. So there exists some action within the support of Xi such that the utility this player gets by simply playing A and others continuing to play their previous strategy itself is a strict improvement over what he was getting when all of them were playing this mixed strategy profile. Okay. This is what allows us to do this polynomial verification. Okay. Because see, this is basically enumerating over this guy's action space. And that's part of the description. I'm not trying to generate a mixed strategy profile. This, how we would do, is not clear without more structures in the game, right? This is basically a probability density function, right? Okay. So with that in mind, there exists a polynomial verification, and so if it's not in Nash equilibrium, there exists a polynomial. If this thing is not the Nash equilibria, then there exists a polynomial description of that evidence, right? This player I and this particular action, that itself will give me a strict improvement. That will give that player a strict improvement. That's the idea. Okay, fine. So now let's move on. Okay, and of course, Brouwer, you know the function f. You're given a point x. You plug to f and see whether it's actually the point moves. That's the evidence of this thing, right? Okay.
A second. I had a question. Sorry.
Yes.
So for the Brouwer function, we also need the function to be polynomial computable, right? Since we're just plugging in the value to check.
Okay, good question. Point. We assume that there exists an oracle which will give me the value of f. The computability of f is not, because the idea is, see, the f is part of the description. So description of f should tell me how f is. The definition of a function literally is, here is the domain, here is the range, here is a point. What is the f value of that point? So when we say the function is part of the input, the way the function evaluates, that has to be part of the description.
Okay.
Okay. Now, here's the thing. That function f, how it is described and so on and so forth, that sort of plays in the role of how big is the input itself, what is the description complexity, and so on and so forth. But that's not what your question was. Your question was, how am I even computing f? Is f even polynomially computable? That's not germane to Brouwer type of question, because the idea is you're giving me the function f itself. All I have to do is give you a fixed point.
Okay, cool.
Okay, so the input consists of f means that there has to be a way of me knowing how every specific point within its domain maps to. Okay, all right. So see, this function NP is like a modified NP. Like literally the word function is used as a modifier. It's NP-like, but with this special characteristic thrown in that we want to find a solution, right? This thing. Okay. So now all of you, I think, know about NP completeness reductions, right? All of you know, even the undergraduate students, can somebody just chime in? Have you all seen reductions? John, so yes, no? Okay.
Yes, ma'am.
Okay, fine. So reductions are what allows us to talk meaningfully. So I just define a class of problems. It could be anything, like I just like whatever. I call it Sushmita. Now, why should somebody be interested in it? Well, people become interested in a particular class if you show that there is an interesting problem that is member of that class. So then the member of the class, so interesting problem, what is that? Well, it could be, it really depends how you define interesting. It could be a natural question that people are interested in, or a question that is not really natural, but it helps us to understand other questions and so on, right? So, and we'll see questions like this that were fabricated literally to capture a particular class. So they are not natural per se, but they play an important role. So that's one thing to say, is to say, okay, this class actually contains an interesting question. But you see, I can always describe a class which encapsulates all interesting problems that I can think of, right? Basically, I take a class which contains all those classes. So naturally, all interesting problems are part of that class. But does that necessarily make the class interesting? Right? No, because it's kind of a trivial thing, right? I can always define a class like this. Well, the next thing to show that the class is interesting is to show somehow that there is a problem which is there's a natural question that is at least as hard as any other problem. Meaning, if I could solve that problem somehow, then all problems in that class would be solvable. Okay, that's the idea of this thing. So whenever we define a class, this notion of we should be able to define, like this is the notion of completeness, membership and hardness. So to show that completeness, we need a natural notion of reduction. So the reduction for FNP is this kind. It's again polynomially bounded. And we say that a search problem L associated with, so remember FNP come with an algorithm and a polynomial function, right? So that's the thing. So a search problem L is in FNP, and it has this algorithm AL, and this polynomial function PL is polytime carp reducible. Carp reducible means for every instance, there's a transformed instance, okay? To another problem L prime, which is also in FNP, and it is associated with the language AL prime, algorithm AL prime, and the polynomial function PL prime. If and only if, so L reduces to L prime, if and only if there exists an efficiently computable function f and g such that f maps the input instance of L input instance, okay, of L into an input instance of L prime. So this is the traditional kind of reduction property that you know, that the function itself, right, should be, the transformation function itself is polynomially bounded. Like I can execute the transformation in polynomial time. Second property is this, that for all pair X and Y, if the problem L prime, the transformed instance that I get fx, if it has a solution y, that's when it will evaluate, that's when the algorithm will say, L prime will say it is yes instance, but when y is a solution of the transformed instance. It means that the original instance to the language L also had a solution. And that solution is basically mapped by this function g applied to the solution y of the transformed instance. Okay, so what g is doing, a function like g is called a solution lifting function. So if there exists a solution for L prime, g applied to y will give you a solution for x. Okay, now the additional property is the following. For all inputs x to the original question L, if the transformed instance does not have a solution, see, does not have a solution, okay, there should be a for all y here, okay, for all y, then the original instance for the problem L should also not have any solution. Okay? This is why these two conditions basically imply that if I could solve L prime, then with using a polynomial amount of overhead, basically I can also solve L within the same amount of time. Why? Because I will take an input X, right? Use the F function. It is computable in polynomial time, F, right? I can execute it and create the transformed instance. Use my algorithm L prime on this, get the answer, apply G, and extract a solution for the original input X for this problem L, right? And if I do the same thing, but this transformed instance Fx has no solution, that guarantees me that the original instance for L also did not have a solution. This is why this means that whatever the algorithm for L prime is, that can be trusted. Whatever that answer is, I can say sort of return back the same answer for L. Okay, and we say that a search problem L is FNP complete. What do you think will be the definition of FNP completeness now? Firstly, the problem L should be a member of the class FNP, right? That's the first thing. Completeness requires membership and hardness. And the second would be that every problem in FNP should be cart reducible in this way to L. So meaning L is at least as hard as any other problem in the class FNP. Okay. All right. So with that in mind, tell me, can I show? Okay. Yes. Why is SAT FNP complete? Is SAT FNP complete? Is the question SAT, is it even a member of the class FNP? We talked about this, right? Yes. If I can make this thing a satisfying solution, a satisfiable formula, and it's satisfying assignment, I create all these pairs that constitute the relation RL, right? Yes or no? That means it's a search thing. And by using the definition of FNP, I know that there's a function. So search, SAT, right? Along with its satisfying assignment, it's a member of FNP.
And the proof we give for Cook-Levin theorem, that's from that we can actually get the certificate for other problems.
Correct. That's right. The Cook's reduction itself was take any NP problem, right? Convert that Turing machine description into a SAT instance. Right? That was the thing. And that is basically the same thing. Solutions get mapped to solution that can be used to get an FNP type certificate for SAT. Okay. Now, let's talk about all these problems that we have been looking at. Nash, Brouwer. Are they FNP complete? Are they FNP complete? Yes. So first, let's try, right? Are they in FNP?
They're in FNP.
Good. They are in FNP, right? Yes. Now the question is, are they hard for FNP? What do you think? So we just have an example. We just now said that SAT is actually FNP complete, right? It is in FNP. So then if Brouwer or Nash, let's talk about Nash. If Nash was FNP complete, then SAT should be reducible using this sort of this description of reduction. SAT should be reducible to Nash.
I have a question.
Yes.
When we talk about FNP completeness or completeness of any sort, we actually need like some base complete result, right? And we can show that the problems we want to be complete, we can reduce. So, I mean, do we have any base complete result in this case?
Yes, that's why I said, right? SAT itself is FNP complete.
Okay.
So the point would be, if I can reduce SAT to Nash using this polytime carp reduction, right? That would show that Nash is also FNP complete, because Nash certainly is in FNP.
Yes, I have a general comment on this. I just recollected that we were talking about like representing the inputs of the Sperner's lemma graph through circuits. Maybe we can try in that direction.
So you want to reduce Sperner to SAT?
Yes.
Okay. Yeah. Fine. So we discussed, right? It's Sperner, Nash, Brouwer. All three are part of FNP. Correct.
Mm-hmm.
So yeah. So let's see. Is Sperner reducible to SAT? Is SAT reducible to Sperner? So turns out, no. And why do you think that is? Any idea? I'm going to write just small p, okay? All these are part of TFNP, right? TFNP is subclass of FNP, correct? We know this, right?
Yes.
Okay. See, the problem is this first
SAT in
condition
itself is not.
yes, SAT is not
TFNP.
Yes, SAT is not in TFNP. In particular, this condition, it is saying that if I were to show SAT is reducible to Sperner, let's take it, right? Basically, we are saying that whenever I find a solution for the Sperner problem, I should be able to extract for all pairs of X and Y, whenever the transformed instance to Sperner has a solution, I should be able to extract a solution for the SAT instance. Okay? But we know that there are instances of SAT that have no solution. These are unsatisfiable formula. But even when you transform it into an instance of Sperner, because Sperner always has a solution, that transformed instance will always have a solution. Right? And then this sort of reduction is saying I will also be able to then give a solution for an unsatisfiable formula. That's a contradiction. Okay?
Yes.
So that's basically the problem with all of these three questions. Nash, Brouwer, and Sperner. They are total problem, and SAT is not total. So this is why it's clear that the class FNP is not where these problems, they are member of FNP, but they are not precisely defining. There's something more there in these problems that there's much more of a structure in these problems, right? That they have the special property that the general class of FNP does not have. Therefore, we need to purpose build, and at that time, there was no known class which seemed to capture the essence of these problems. So, of these problems, meaning these total search problems, these category of problems which always have an answer, but you're trying to search for a solution. So, they needed to purpose build a computational complexity class to understand these problems. Now, quickly speaking, you might wonder, why am I trying to do this? Like, why am I trying to build a computational complexity class such as this? Because you see, it is like you can imagine how huge mathematics is, and theoretical computer science is a very small portion of it, but often the possibilities of problems, they like, okay, you can enumerate the number of problems that we have considered through history, but still it's a gigantic list of it, and one can always come up with more and more problems, right? So in a way, the number of problems worth studying is like an infinite thing, but to manage it in a very sort of a to keep things manageable, we notice one thing, that some problems are basically a known problem, just the language is different, but essentially they are equivalent. That's the idea of computational complexity. We want to be able to categorize problems in ways that saying something meaningful about one tells us immediately something meaningful about all those problems that belong to the same category. So that's the idea behind the computational complexity, and in particular, why we are trying to find a class for these total search problems. Okay, that's the thing. Okay, so how would we go about it? So it's basically, you will want to find. Okay, so we take hint from, this is where, in order, we see that Sperner, having a solution for Sperner gives me a solution for Brouwer. I have said this, I have not shown it to you, but I mean, we talked about it the sort of in a very sort of hand wavy kind of way. So for the purpose of defining, giving a computational complexity theory for these problems, what we basically try to do is use Sperner to extract what we want to try to say is, we want to be able to capture the some sufficiency condition that allows a solution for Sperner to exist. Okay, and we want to extract that out and create a problem that captures this, and then that problem is the problem that will capture, that would neatly capture all these problems because of their otherwise equivalence. We know that Sperner, Brouwer, and Nash are all equivalent. So using Sperner, I want to extract a condition that would then be made into a problem, and then that problem, okay, will basically will be equivalent to all these problems. That's the idea. Okay, so this is where the PPAD completeness comes in. Now, I asked you all whether can you find a solution for Sperner, either way, whether if it's given an explicitly or implicitly, whichever way. Do you know, can you tell me how one could find a solution for Sperner, this triangle? Okay, maybe it's not obvious, but once I tell you, I think you will see that you have seen this kind of argument many places. It's just not in this kind of way, so here. Okay, so for just convenience, I'm going to assume that this outside grid lines, okay, this outside boundary, these boundaries, here we are only going to use blue. So Sperner was not preventing me from using a second color, but we will assume, suppose that this boundary only uses blue, this boundary only uses red, and this boundary only uses yellow. Okay. Notice that this particular restriction does not make the problem any easier. Why? Does this sort of a thing, does that, if I do it like this, would it make it any easier to find that trichromatic triangle?
This could have been the valid coloring in the previous step also. So
okay,
the problem is same as what we had earlier.
But why?
The increase in size is only 4 and
so
Sanjay,
okay, what you're saying is fine in the sense that yes, this could have been my valid boundary coloring, right? But maybe for whenever the boundary coloring has this restricted property, it is possible to imagine that maybe finding that trichromatic triangle is easier now. But why is that not the case? So you were saying something, Dipro?
I was saying, if if we're stripping down the border, then again we are getting rid of some polynomial amount of vertices, but the inside one, the internal ones, we still have to find the triangle, right?
Yeah.
I do
Basically, it's
not have
this
a very
idea.
formal argument.
Yes. Basically, take one of those general things, right? The general thing, and put an outside this sort of thing. You're still having the trichromatic triangle still lies within this. Only outside I have a property, and the moment I enter this line, right? This thing, I'm in the old setting, right? So this is
So
one.
is it like,
And the triangle lies somewhere inside. So I'm back to this as general a question as possible. That's basically the idea. Because clearly the trichromatic triangle does not lie on this grid lines, no? Everything is colored the same here. So the only way I can find the trichromatic triangle is inside. And over here inside, these are arbitrarily colored. There is no, I can't restrict these colorings to be anything. Therefore, putting this outside restriction here, it does not make the problem any simpler. Okay, but it allows me to do like start my argument that I'm going to say next. Okay, all right. So now what I'm going to do is, see here the point was this side will only have red and this bottom will only have yellow, and over here this is common to this right hand boundary as well as the bottom boundary. So I say that, okay, this has to be colored blue. Okay, so with that sort of an assumption, okay, so I create a vertex outside here and color it with a third color that is not represented on this edge. Okay, that's the thing. So what I've done is created an artificial triangle, a trichromatic triangle. Okay, now starting with this, what I'm going to do is try to find the next trichromatic triangle. Now, because this is the only one that is outside, the next trichromatic triangle I find will have to necessarily be inside. That is the idea. Okay, so now how do I start this search? What I'm going to do is basically tell you how I can sort of do this search. So it's going to be like a guided path, where the path basically has to follow some rules when I can basically cross over the edge and so on and so forth. So the rule is the following. Okay, so transition. So from one triangle to another, I can cross over if they have a boundary like this. Let me draw this. I think it should have a picture somewhere here. Okay. So let's say this is a yellow, this is a red, and okay. So see, if I already find a triangle like this, well, then I have already found a trichromatic triangle, right? So I don't have to do anything. So if this is not found, it must mean that two of the three vertices have the same color. Yes. So I say, let's say this is yellow. This is this. And the next triangle is of this kind. So I basically can travel through an edge if, see, I'm going from this side to this side, if the yellow is on the left. Okay. Now I have entered this triangle. Where can I go next? So I'm here right now. I have entered through this because the left is on the yellow is on the left hand side. So what can I do now? Which way can I go? I can't go this way because this edge is both yellow. I can actually go down this way. This is allowed. Whatever this triangle is, either this triangle is a trichromatic triangle, or it has some colors repeated. Either way, I can actually go from this triangle to this triangle. That's the rule of traversal, nothing more. Okay. All right. So now, going like this, let's see this. So I entered this through this door. Okay, here the picture is it's saying, so, okay, so the yellow is on the right hand side here. Okay, so I said the rule of traversal is yellow being on the left hand side, but in this diagram, we are seeing that actually what they're doing is the traversal is the rule is the opposite, the yellow is on the right hand side. But it really does not matter. What matters is that when you're first entering through this artificially constructed triangle, with what was to your left? Here it was red. So actually I should have given the example using this. I forgot that I actually see red on the left and not right. So when I first cross this edge, what I see on the left, that and the edge I cross, that determines what my transition rule will be. So therefore, once I enter this triangle, this grid, the next rule here, next would be where can I go? Well, I can go here, right? Because red is on the left hand side. So I'm crossing over this. The next, I can again go here. Then where can I go? Again, I've not yet found a trichromatic triangle, so I have to keep going. Next, where can I go? Anybody? I can actually go this side, right? I can't cross over this, because these are yellow. So I can actually move like this only. That's the only unique pathway for me. Do you agree? That it's not like I have multiple ways to proceed. Each place, either I have found a trichromatic triangle, the triangle that I have just entered, or there is an exit way for me. Okay, so now once I enter here, I have found a trichromatic triangle. Yes? So starting from this artificial triangle, I have actually ended up at a trichromatic triangle. Magic. No? Is it magic? Or have you seen this kind of argument before? So now, so here is the thing though. While this triangle was artificially constructed, this is an inside triangle. Now, you can see for yourself that somehow, if I find a trichromatic triangle in this grid, I can do the same type of search and end up at another trichromatic triangle. Why is that?
Because in this path, I keep on going along this path till I have a trichromatic triangle. I began with red and yellow. So, like, if I do not find one such trichromatic triangle, I end up basically at the last square, which again has like blue in it. So I get the trichromatic. I'm pretty guaranteed to get a trichromatic triangle if I move along this path.
And why is it that, okay, you're saying I will actually end up at this blue, because we know that at least these boundaries have blue vertices, right? So even if inside there are no blue vertices, I'm definitely going to find a trichromatic triangle on the boundary. That's the point, right?
Yes.
Okay, so what is the guarantee that you will actually, the way you entered, you would be able to find a trichromatic? You can get a all blue edge here. Why would that?
But I reached the last square traveling through this this kind of path, that directional path that I
via red yellow path, via red yellow edge, right? So, yes.
Yeah.
I crossed
so
over.
I would reach there if I only have red yellow vertices.
Correct.
So that means I will
can't see the fact that I got to a blue vertex wherever it is because I came via red yellow edge. And therefore that itself gives me a trichromatic triangle, right? So so basically the trichromatic triangle exists because of this kind of a thing. And the point is so it always exists. So Sperner also said it, but the point is how to find it. But this sort of a search process, this kind of a thing, I create an artificial triangle and find another one inside. And then if I have any other trichromatic triangle, starting that, I can always get to another trichromatic triangle. Okay. This thing is what tells me that there must be odd number of trichromatic triangles inside. Because when I started, I ended up in another trichromatic triangle, right? So there are basically pairs of them. So in total, they're even. But one of them was an artificial one, which I constructed outside. So inside there must be an odd number. Yes? And that's what Sperner says. Now, you tell me, Have you seen this sort of an argument before, where you start from a vertex and you end up at another vertex which has some type of special property? See, these are the other examples of this. This is a good thing. See, if I just start from some triangle which is not trichromatic, but my transition rule remains valid. This, I am crossing over a red-yellow edge with red on the right-hand side. Okay, if I just did that, there is a chance such an example here exists. I basically go around in a loop. This is possible. But see, the starting point itself was not a trichromatic triangle. All we are saying is if you start from a trichromatic triangle, then you will end up in another trichromatic triangle. Right? If you don't start from a trichromatic triangle, you might just move around. Okay? All right. So tell me, where have you seen this sort of an argument? This directionality of the path and so on. This should give you a hint. It's basically what happens in any directed graph. Starting from a source, you always end up at a sink. So sources and sinks appear in pairs. Right? So whenever you start with a source, if the graph was entirely given to you explicitly, you can look at every vertex and see where is a source, right? You can find a source. Source vertex is one which has in degree 0. And starting from there, you can get to a sink. So source and sinks appear in sort of this paired wise sort of thing. Yes?
Yeah, this is like the argument where you have even degrees for each vertex, and then you have a Eulerian path. It's a similar kind of argument. Like we travel via edges.
So Eulerian path is it's much like Eulerian path would be where you're visiting every edge. I am not visiting every edge. I did not cross every red yellow edge. Right? Okay. The point here is this, something to note here. The graph that we were looking at had much more special structures. Okay. And the path navigation that I did had much more structures than, so using that red yellow edge crossing this thing, we said, right, that there's only one unique triangle that I can end up when I cross over an edge. So I don't basically there are not possibilities that I can end up in this triangle or this triangle. There's only a unique red yellow edge in which the red falls on the right hand side. Or sorry, left hand side. That was my crossing, that was my transition property. Right? So basically, this sort of thing can be abstracted into just thinking about a graph, a directed graph with some additional properties, which is that an in-degree of a vertex is always at most 1. Either you have no in-degree, like that artificial triangle we had, right? That's where we were starting. So that's a source. And even if you have an in-degree, you're basically, your in-degree is exactly 1. So you have only one neighbor vertex from which you can enter this vertex. Similarly, there's at most one vertex to which you can exit. So all the vertices in this graph are those triangles. If a triangle is itself, unless that artificial triangle is a source, all other trichromatic triangles in the graph are sink vertices. You are not allowed to leave. You can't leave. So they are sinks, right? And all other vertices which are not trichromatic triangles, they must have red and yellow repeated at least twice. And from them, we know that they will have at least one in neighbor and they will have at most one out neighbor. Okay. So this particular graph, when you have this sort of degree constraints, the graph has a very simple structure. It consists of paths or cycles or a bunch of isolated vertices. Okay. Notice the paths have a starting point and an end point by the definition of a path. We are talking about maximal paths. The start point would be a source, right? This thing, trichromatic triangle, and the source would be another trichromatic triangle, right? Okay, so now, so this is why I was asking, if you get a graph, finding source and sink pairs is easy. The reason this question becomes hard is because we are not given the whole graph. We are basically given that circuit, that implicit description of a graph. Okay. Okay. So, okay. So the source and a sink is what he's calling here as an unbalanced node, because it does not, it has at most one, like it does not have both an in neighbor and out neighbor. A source has no in neighbors and a sink does not have any out neighbors. So basically finding trichromatic triangles in this problem becomes, reduces to finding sources or sinks in this graph that we just now, in this directed graph that we just now created. Okay. Okay. So now this property. So what happened is Sperner has now reduced to a graph, to testing a graph property where the graph is not implicitly described, where the graph is not explicitly described. You agree? That's finding a solution for Sperner will imply a source and sink pair in this directed graph. A directed source and sink pair in this directed graph will account for all the colorful trichromatic triangles in the Sperner diagram. Okay, so this is where we get a definition of a class, which came to be known as PPAD. People have joked that Papadimitriou defined it, and he defined it sort of after himself. But the PPAD has an extended name. It is polynomial parity argument in directed graph. P for polynomial parity argument in directed graph. Okay. So you have an exponentially large number of vertex set. The graph itself, this graph, not the Sperner coloring graph, but this graph itself is defined by this P and N node. And you basically give a node ID here, and this P gives you a potential predecessor of the node, meaning a potential in neighbor of the node. And N basically gives you the next successor. Okay. So if V1 and V2 are adjacent to each other, in particular, if V1 is an in neighbor of V2, you must have this property. That is, the P circuit P applied to V2 should tell you V1, meaning V1 is a predecessor of P, and also the next guy after V1 is V2. Okay, both of these should be true. That would encode an edge, V1, V2. And if V1, V2 is an edge, this would be true. Okay. Now, the question that we ask is this thing called end of the line. Given two circuits P and N, we assume that all 0 bits. That's the name of a vertex. It's just a special name, does not matter. It's just something to get us started. It is an unbalanced node. So imagine 0 to the power n is this sort of artificial triangle we created. Okay, it's an unbalanced node. And the point is, starting with an unbalanced node, find another unbalanced node. Otherwise, if such an unbalanced node does not exist, then you basically say output this thing, the first unbalanced node from which you started. This is the end of the line problem. And sometimes it's called EOL. At least when talking about it, it's customary to call it EOL. Is the problem clear? Okay. So, sorry, the main thing got. Last line. So, PPAD is a problem class, a class of problem, such that it contains such problems which are in FNP. So, it's a subclass of FNP. But end of the line, this problem is a hard problem for this class. In other words, every problem that belongs to PPAD should be cart reducible to this end of line problem. Okay. With this definition in mind, this definition was given in 94, Papadimitriou showed that end of line is actually reducible to Sperner. Okay, first and foremost, given the way we have actually described, you agree that, I don't know what this slide is, but let's just see. Okay, so this is how it looks. Okay, this is how this is. But let me just say, let us just ruminate over this for a minute. That. So you guys have a class after this, right? So I'll just end at 11:30. Okay, it's already 11:30, but just give me 1 minute. I'll just end it here. So what we have is Nash is reducible to Brouwer because of the proof of Nash, right? If I could solve Brouwer, I could use that fixed point to define Nash. Brouwer proof follows from like Brouwer theorem was using Sperner's lemma. Okay, so this is what this is. You agree? Now Sperner, basically the idea behind Sperner, that there is this trichromatic triangle and so on, is basically finding a directed path in this specially constructed graph, the source and sink pairs, reduces to this end of line. You agree? And end of line by definition, this is just a notation, captures the class PPAD. It is not only in PPAD, but it is also as complete for PPAD. It's at least as hard as any other problem in PPAD, right? And PPAD itself belongs to the class TFNP. Okay, I should not use this. So, okay, so this is a bit of this thing. When I write it this way, what I'm trying to say is PPAD is a class. So this basically means that EOL is complete for this notation, okay, as complete for PPAD. And PPAD as a class belongs to TFNP, which of course is again a class inside FNP. This schematic picture is clear from what we have discussed so far. Okay. Now, what Papadimitriou showed was, he also showed that that EOL is reducible to Sperner. This is not very surprising. The intuition should be fairly clear. EOL precisely captures the property of Sperner, and Sperner basically is a problem which generalizes to AOL. And so this this is by definition, and this sort of a result should not, like, it's okay, it's believable, right? Okay, so this was known, as well as what else was known? Something else was also known from Papadimitriou's work from 89, I believe. Yeah. Now, what these people showed, Daskalakis and others, so this is basically the schematic diagram, okay, that I was drawing there. This thing, so these straight arrows basically means that Nash reduces to Brouwer, Brouwer reduces to Sperner, Sperner reduces to PPAD. PPAD, or like the standalone problem for canonical problem for PPAD, is EOL, and that falls within the class of FNP. Okay. Now, in this 2006 work, it's a path-breaking work, what they showed was the other direction, that EOL is no harder than Sperner, or that Sperner is at least as harder as this. And then Sperner, this was known, but okay. And then these dashed arrows, okay, the one that is that PPAD is no harder than Brouwer, and PPAD or EOL is no harder than Nash. So all this diagram, this was known from before, and what this was shown in 2006 is it's 18 years, right? Together, you basically get these equivalences. Okay. All right. I think I'm going to stop with this. And tomorrow we will wrap up all this discussion. Basically, what we will see is this part. We will discuss briefly what arithmetic circuit sat is and how this sort of this problem reduces to problem instance for Nash. And we are not going to go into all the details of it. This is several sort of stages of work, but it is going to, if one of you want to do a partial presentation during a student presentation on this, I can suggest some reading and presentable material from Daskalakis's PhD thesis and other things where we can dig a little deeper. So I'll put some of these resources online and on the website, and you can check whether it's something that you would be interested. It's a very interesting line of work, obviously, but it takes a lot of time and sort of merits a deeper discussion. So with that, I'm going to end today, and I'm going to see you all tomorrow. If you don't have any questions, then we can just sort of end with this.